Hey guys, we just reached noon here whenever I'm recording the video. So yesterday I apologize for the 3.2 video. I just felt like I was just lagging through it. So hopefully today will go better. I like trigonometric functions, and so taking a derivative of them should be a little bit more fun for me. I want to show you where some of the derivatives come from today. Instead of just saying the derivative of sine is this, the derivative of cosine is whatever the derivative of cosine is. Okay? So I'm going to go back to my sine function. My sine function is going to be this wavy line right here that just oscillates between -1 and +1. So what I'm going to do now is I'm going to find the slope of tangent lines and plot those and then connect the dots. Well, the easiest slope of tangent lines I can get are these ones that are 0. Here, and here, and here. Okay? So the slope of all these tangent lines are 0. And so my new line, this red line right here, is going to be actually the same x value, but then just the slope, or if you want to think of it as f prime of x. So I'm actually going to be graphing my derivative. Well, I need a few more points than that. I don't want to just draw a horizontal line going across. So if I look right here, that slope is pretty nice. It's looking like it's 1. The slope here is looking like it's going to be -1. Oops, put that in the right spot. I did. +1, -1. Huh. This red line look familiar to you at all? Kind of looks like the sine function, but instead, it's starting up here on the hill. It's just going to be my cosine function. So what I have is, if I'm taking the derivative of sine, it's just going to be cosine x. So now, I can mix in all my differentiation rules with this. I can do a product rule, a quotient rule, or just a power rule with this. So let's see how this example would pan out. So I'm looking at it, I got a product right here. I got the product of two functions of x. So if I'm looking to differentiate this, take the derivative of it, remember that's just going to be the derivative of my first term times the second term plus my first term times the derivative of my second term. The derivative of my second term, we now know that the derivative of sine is going to be cosine. There's not just a whole lot I can do with this. If I wanted to pull out an x, I could. You can write it without the parentheses. That might make it look a little bit better. But I would really just accept this. This is perfectly fine. And so this would be the derivative of x squared plus, or x squared times the sine of x. And so using the same method that I showed you where the derivative of sine is going to be cosine, I could also show you that the derivative of cosine would be negative sine. I'm gonna kind of skip that in this video and not show it, but I'd like to derive for you the derivative of tangent. Derivative of tangent. Remember that tangent is just going to be sine x over cosine x. And now that I've spilled the beans on what the derivative of sine x is and what the derivative of cosine x is, I can find the derivative of tangent. Now, be careful. I switched this, and I have a quotient, meaning I need to use my quotient property in order to find the derivative of sine x. My quotient rule, not my quotient property, quotient rule. So my quotient rule says that I need to take the derivative of this top first. The derivative of sine, we said was cosine. Okay. Times the bottom minus the top times the derivative of the bottom. The derivative of the bottom is right here. Derivative of cosine is just going to be negative sine x. And don't forget about your all over bottom squared. Oh, hopefully this will clean up some. See, I got cosine times cosine. Let's just go ahead and call that cosine squared. I got a negative sine times a negative sine. That's going to be a positive sine squared over cosine squared. I didn't really clean up just a whole lot. But look what I have on top. Dig way back into your pre-calc memories now. And remember that sine squared plus cosine squared is my first Pythagorean identity, which is going to be 1. And then that gives me yet another Pythagorean identity, which is secant squared x. So yes, I have just proven that the derivative of tangent is secant squared. And so as you can see, I could go through and do the other 3 trig functions, cosecant, secant, and cotangent, the same way. All right? It's going to ask you to do some of those in your homework. I'll just go ahead and tell you what they are so that you can work your way towards it. So, for instance, I know the derivative of sine, we said it was going to be cosine. Derivative of cosine is negative sine. And the derivative of tangent is going to be secant squared from what I just proved. So using the same logic and using some quotient rules, derivative of my cosecant is going to be negative cosecant. I misspelled cosecant. Negative cosecant x, cotangent x. Derivative of secant x is going to be secant x, tangent x. Derivative of cotangent is going to be negative cosecant squared x. There are some patterns in here. You just pause the video for a little bit, look at the patterns with this. I'll give you one pattern. Look at everything that is a cofunction. Cosine, cosecant, cotangent. They're all negative. All the rest of them are positive. There's some other patterns you can look at. I'll let you discover those, and we'll be talking about it in class. So now, I will be able to differentiate any trig function. And I can do it within a product, a quotient, or can't do it if it's raised to a power just yet, but we'll get there by the next video. So I want to differentiate this function and then find horizontal tangents. So let's go ahead and differentiate it. I have a quotient, so I'm going to take the derivative of the top, and so the derivative of secant x is secant x tangent x. That's secant x times tangent x. I'm just not saying the times in there. I'm getting kind of lazy. So the derivative of the top times the bottom minus the top times the derivative of the bottom, derivative of 1 plus tangent x. Well, derivative of 1 is going to be 0. Derivative of tangent x is secant squared x all over 1 plus tangent x, all that to the second power. I'm really not going to expand that unless I just get a real big ink pencil to write out 1 plus 2 tangent x plus tangent squared x. I don't see how that's going to help me at all. I'm going to have to clean this up. You seeing anything? It might help if I distribute. Why don't I distribute on top? Let's do secant x tangent x times 1 is secant x tangent x. And then secant plus secant x times secant x tangent x times tangent x would be tangent squared x. Kind of give you an illustration of what I did there. I just distributed secant x tangent x through those parentheses. And here, it wouldn't be the second power anymore, would it? It would be to the third power. All over the bottom part squared. Now, I've only got 3 terms on top, and I notice that they all have secant in common. So this secant that I just pulled through here and pulled through, I'm actually going to factor it back out. It looks kind of weird. This back one doesn't have a tangent x, so I can't pull out a tangent x out as well. Instead, it's going to be tangent x plus tangent squared x minus, I'll pull that as secant, so it's going to be secant squared x. almost had you guys do this problem on your own. I've been going back and explaining a lot. I do think it simplifies more. Now, if you got it to here and I was just asking for the derivative, you're probably going to get full credit. But this does simplify some more. I have another one of my identities from last year that said that 1 plus tangent squared was equal to secant squared. Meaning that if I subtract off the secant squared and subtract off the 1, I would get tangent squared minus secant squared would equal negative 1. Meaning that all of this would just equal negative 1. And you might be looking at it saying, well, I bet you that'll somehow cancel with that bottom. It doesn't. We're actually done right there. That would be as far as this one would simplify. But I need to find where the horizontal tangents are. Right now, room down here at the bottom, so I'm going to move this up to the top. So remember, my horizontal tangents are going to be where my derivative is, where my slope is equal to 0. So that would just be where my derivative is equal to 0. Well, if I have a fraction and I'm wanting it to equal 0, I just need it so that the top is equal to 0. So I'm just interested in where, and it's already factor forming, where secant x would be equal to 0 or tangent x plus 1 would equal 0. Either one of those. Well, I don't think secant x is ever going to equal 0. Secant x was on my little Lego hands off of my cosine function. That never did equal 0. Let me change colors. That never did equal 0. It never came down to grace the x-axis. All the Lego hands in the standard position stayed above and below that axis. However, I'll subtract 1 right here. Tangent x does equal negative 1 in some places. Okay. Oh, wait a minute. I messed up somewhere, didn't I? Oh, here we go. I miswrote this. It's good to see me make mistakes. Minus 1. So it'd be where tangent x is equal to 1. Well, on the unit circle, tangent x equals 1 at pi over 4, 5 pi over 4. I can keep going around. 9 pi over 4. Let's see, what am I adding there? I'm just adding pi each time. So 13 pi over 4. I can keep going on. So every pi over 4 is what we wrote last year, plus 2m pi. And every 5 pi over 4 plus 2m pi. I would accept that answer. It is a little bit redundant. I could have just said pi over 4 plus n pi, since the period of tangent is just pi units long. I'm about done. It's going to be another short video. I think normally in class we just do all this in one day. It doesn't take us very long. I think I'm going too far on my circles. There we go. So an object is at the end of a vertical spring and it's stretched 4 centimeters beyond its rest position. And it's released at time equals 0. Okay, so imagine taking this spring right here and you're pulling down on it. Okay, you've got a picture of it right there. So it's going down, and so the downward direction on this is going to be positive. So I'm able to have a position function right here. My position function is going to be 4 cosine x. That makes sense. If it's 4 cosine x, it's going to be cosine because it's just going to be oscillating up and down between its values. It's just going to bounce. I want to find the velocity and acceleration, and then I'm going to analyze the motion of the object. Ooh, I think so, huh? Okay. Well, my velocity, I'm just going to try to squeeze it in here, is going to be the derivative of my position will equal my velocity. Now, every year I have people say, hey, you need to multiply that by, you need to do a product rule there. And I assure you, I could do a product rule, but remember, this 4 can actually go out in front of my derivative. I can just do 4 times the derivative of cosine x. Derivative of cosine x is negative sine x. So that would be the velocity. So if I want to know what the velocity is at 2 seconds, I can just plug in 2 in for that x and tell me the velocity. And as far as the acceleration goes, I'll go to blue. Remember, the acceleration is just the derivative of the velocity function, which is just the double derivative of my position. So if I take the derivative of this negative 4 sine x again, I'm going to use a trick where I bring the negative 4 out in front of my derivative. And I can just take the derivative of the part of sine x, part of my function that has the x in it. Derivative of sine x is going to be cosine x. So it's wanting me to graph this. Let's see what I can move up here without having to rewrite. So there's one of them. Here's my acceleration. I'll rewrite the rest instead of moving it. This is my velocity. Stop time. How about that? And then here's my acceleration at time t. And I had a position function. Let me look at my notes here. I'll go back to my position function. It's going to be 4 cosine t. So let's draw this the best that we can, leaving everything, try to leave everything to scale and see what we get. So 1, 2, 3, 4. That's where my spring is going to start on that position function. 4 cosine t. Okay, and over time, it's just going to come down, all the way down to 1, 2, 3, 4 cosine t, and then back up. It reaches back to this peak at 2 pi. I didn't come close to making my x-axis to scale, so don't count that out and see how close I am and not. But I know a couple of points in here that I'm going to use for references. So that would be pi. Here I have pi over 2, and I have 3 pi over 2. Okay, next, red, I'm going to let that be my velocity. Okay, so that says it's going to be 4 sine t, meaning I'm going to start here at the origin. Let's see, it reaches its peak right here at pi over 2, comes back down, all the way down to here, and ends back at the origin. That would be 1 complete cycle. And then finally, I have my acceleration. My acceleration is going to be negative 4 cosine t. So that's just going to be a reflection of this black line that I have. Let me get some reference points here. I'll be ready to draw it. Coming down, comes up, and it comes back down. There is all 3 of my functions. I got my position function, I got my velocity, and I've got my acceleration. So what do we notice? Just pretty much anything you can notice will be fine. Look at my red though. Look at my red. Right here, the object's going to be moving at its fastest. Okay, within the first 6.28 seconds. So right here, this red line is my velocity. My velocity is the highest right here on this hill. So at its fastest, okay, let's see what's happening at the fastest. The object, look at the position right here. The position right here, right, is that my position? Position's black, I'm sorry. The position right here is actually at its equilibrium. It's not being stretched at all. Up here it's being stretched, and down here, when it reaches down here at the bottom, it's being stretched. But the spring is actually at its normal position, not stretched either way, whenever the object is moving at its fastest. We just say at its fastest, the object is at its equilibrium. Oh boy, got a math teacher trying to spell equilibrium here. Equilibrium. Oh, all right, close enough. Like I said, anything that you see on here, the object is, it's kind of neat right here. The object is speeding up at its fastest whenever the velocity is neutral. The velocity is zero. Or you could say whenever the spring is being totally stretched the other way. And so several things you can get from here. It'll kind of cue you as to what to find and what you need. All right. All right, last up, this won't take very long. We're just going to work our way all the way down to the 27th derivative of cosine x. Yeah, the old guy says it's not going to take very long. We don't have to work this out 27 times. Well, let's just start and see what happens. So my first derivative, so it's going to be negative sine x. See, it's fast. The second derivative, let's say derivative of sine is cosine, but then I have a negative in front of it. So again, I just did this negative. Let me kind of illustrate what I'm doing with that. Okay? My second derivative is going to be the derivative of negative sine x. And so what I'm saying is that this negative can come out in front of the derivative, and I can just take the derivative of sine x. So the derivative of sine x is cosine x, but it has a negative out in front. I've kind of mentioned it a couple times in this video, but that's the idea of the gist of what's going on. Now, the derivative of cosine x is going to be negative sine x. So I end up with a negative sine x, which is a positive sine x. All right. The fourth derivative of sine x is going to be cosine x. See, we're almost there. We're almost a fifth of the way there, but wait a minute. I get to here, and I'm just hitting a loop. I've already found out that the derivative of cosine is negative sine, which is what I just found. So what I can actually do is jump ahead a little bit. And because evidently, like this is, if you want to think about it, this is like the 0th derivative. I don't know if that's even the correct notation for it. But every 4 derivatives, I'm coming back home to cosine x. Meaning that every multiple of 4, so the 8th derivative is going to be cosine, the 12th derivative is going to be cosine, the 16th derivative is going to be cosine, the 20th derivative is going to be cosine, the 24th derivative is going to be cosine. And if I'm just looking at working my way up to the, let me do that a little bit different. Let me put that here. This is going to be equal to the 24th derivative of cosine. So if I'm wanting the 27th, I can just count my way down. So this negative sign right here, this is going to be the 25th derivative. This negative cosine will be the same as the 26th derivative. And finally, this sine of x right here is my 27th derivative of cosine. It is my final answer. And so I did not have to work it all the way to 27. I just had to find that pattern they were using. Work some of these. You're going to have to practice these in order to get used to working the quotient rule and the product rule within these new rules that I told you for trigonometric functions and finding the derivatives of them. So have questions ready for me, and I'll catch up with you guys next time.